Our story begins not in the mill, but beneath it, miles away in some cases, deep in the belly of the earth, where the air is thick with dust and the darkness is absolute, except for the flickering oil lamps carried by men who have never seen the inside of a classroom. Iron ore, hematite primarily, though sometimes magnetite or limonite. These are not names the miners know. To them, it is simply the ore or the ironstone. Reddish-brown rocks, sometimes with a metallic sheen, heavy for their size, dense, and cold to the touch. The miners wake before dawn, always before dawn. In winter, they may not see sunlight for weeks at a time. Down into the mine in darkness, up from the mine in darkness. Their hands are permanently stained with rust-red dust that no amount of scrubbing will fully remove. It gets into the creases of their palms, under their fingernails, into the fine lines around their eyes. The mine shaft descends at an angle, sometimes gradually, sometimes steeply. The wooden support beams creak and groan with the weight of the earth above. Every miner knows that sound, has learned to distinguish between the normal settling creaks and the ones that mean danger, that mean get out now. But mostly they don't think about it, can't think about it. The mind can only hold so much fear before it has to set some of it down and leave it behind. The ore deposits form in veins and pockets, following ancient geological patterns that the miners have learned to read like sailors read the stars. A certain coloration in the rock face means the vein runs left. A particular type of stone means dig down. Knowledge passed from father to son, master to apprentice, in languages and dialects that will be extinct within 2 generations. The extraction process is brutally simple. A man, usually young, with the strength still in his back and shoulders, swings a heavy pickaxe again and again and again, 8 pounds of iron on the end of a wooden handle, coming down with all the force he can muster. The rhythm becomes meditative after the first hour. Your muscles scream for the first 30 minutes, then go numb. By hour 2, you've found the rhythm, and you can keep it up for 6, 8, 10 hours if you have to. And you do have to. The ore breaks away in chunks, some small enough to lift with one hand, others requiring 2 men to lever onto a cart. Each piece is examined briefly. The miners can tell by weight and appearance whether a particular chunk is rich or waste rock. The good pieces go in one cart, the waste in another. Nothing is wasted, but some things are more valuable than others. Once the carts are full, and a full cart weighs anywhere from 500 to 800 pounds, they must be moved. In the earliest mines, this meant human power. Men harnessed like draft horses, leaning into leather straps, pulling the carts up the sloping tunnel floors. Later, pit ponies, small, sturdy horses bred for the work, spending their entire lives underground. They go blind eventually from lack of sunlight, but they know the tunnels by heart, by the feel of the floor beneath their hooves, by the echoes of their own breathing in the confined spaces. The ponies are fed and watered in underground stables. Some never see daylight from the time they're lowered into the mine as foals until the day they die. The miners are gentle with them, surprisingly so. A good pony is worth 3 men in terms of the work it can do. And, unlike men, ponies are expensive to replace. The journey from the working face to the surface can take anywhere from 30 minutes to 3 hours, depending on the depth of the mine. The carts travel in trains sometimes, 6 or 8 linked together, winding through the tunnels in the darkness. The temperature rises as you ascend. The deep mines are cold, surprisingly so. The Earth's natural temperature, somewhere around 50 degrees Fahrenheit, regardless of the season above. But as you climb toward the surface, you begin to feel the weather again. Summer heat pressing down through the earth. Winter cold seeping in through cracks and shafts. The miners develop a sense for weather they cannot see. They can tell you if it's raining on the surface by the way water drips through certain seams in the rock. They can predict storms by the way the air pressure changes, makes their ears pop, makes the oil lamps burn differently. At the surface, finally fresh air, though it's full of coal smoke and ore dust from the processing yards. The ore is dumped from the carts onto enormous piles, sorted roughly by quality. The best ore, richest in iron content, goes in one pile, medium grade in another. Low-grade ore might be left in a separate heap, only processed when prices are high enough to make it worthwhile. Now begins another journey. The ore must travel from the mine to the mill, sometimes just a few miles, sometimes 50 or more. In the early 19th century, this meant wagons, heavy freight wagons pulled by teams of draft horses, 4 or 6 horses per wagon, plodding along rutted dirt roads at a steady walk. The wagons are built sturdy, had to be. Iron-reinforced wheels, thick oak planks for the bed, every joint doubled and braced. Even so, they break down regularly. Axles crack under the weight. Wheels lose their iron rims. Harness leather snaps. The teamsters who drive these wagons are a breed apart. They know every inch of the roads they travel, know which ruts to avoid, where the bridges are weak, where the road washes out in spring floods. They sleep under their wagons at night, wrapped in wool blankets that smell of horse sweat and wood smoke, waking every few hours to check on their animals. A team of horses can pull about 2 tons of ore, maybe a bit more on level ground, less if the road climbs. They walk at roughly 3 miles per hour, which means a 20-mile journey takes nearly 7 hours, not counting rest stops. The horses need water every 2 hours in summer, hay and grain at midday and evening. Some mills are built along canals or rivers, and in those cases, the ore travels by barge. A single barge can carry 50 tons or more, pulled by a team of mules or horses walking along the towpath. The barges move even slower than the wagons, perhaps 2 miles per hour, but the capacity makes up for the speed. The canal system is its own world. Bargemen live on their boats, entire families sometimes. Children are born on the barges, grow up knowing the rhythm of the water, the names of every lock and bridge and tunnel along the route. They speak in their own dialect, use words that make no sense to people on shore. When the ore finally arrives at the mill, it's dumped again into stockpiles. These piles can be enormous, hundreds of tons sitting in open yards where rain and snow and sun work in them constantly. The weathering actually helps in a way. It breaks down some of the impurities, makes the ore easier to process. The stockpiles are organized with surprising precision. Different grades of ore in different locations. Ore from different mines kept separate, because each has its own characteristics, its own percentage of iron, its own particular mix of impurities. The furnace master needs to know exactly what he's working with. Young boys, sometimes as young as 8 or 9, work in these ore yards. Their job is to break up the larger chunks with hammers, sort out obvious waste rock, keep the piles neat and accessible. It's hard work, but not as dangerous as the furnace or the rolling mills. The boys see it as a stepping stone. Do this for a few years, prove you're reliable, and maybe you get moved inside, get a real position. The ore sits in these piles sometimes for weeks, sometimes for months, waiting for its turn in the furnace, waiting to be transformed. The blast furnace dominates the mill like a cathedral dominates a medieval town. It rises 50, 60, sometimes 70 feet into the air, a massive tower of brick and iron, wider at the bottom than the top, shaped like an enormous bottle. It radiates heat that you can feel from 100 yards away. On cold winter nights, men who live nearby say you can see the glow from miles off, like a second sunset that never quite goes down. Yea, the furnace never goes out. This is crucial to understand. Once a blast furnace is lit, it burns continuously for months, sometimes years. Shutting it down and restarting it is enormously expensive and time-consuming. The bricks must be heated gradually or they crack. The whole structure must reach operating temperature slowly, carefully, over days or weeks. So the furnace runs day and night, every day of the year, fed constantly by men working in rotating shifts. Christmas Day, New Year's, Easter Sunday, it makes no difference. The furnace doesn't observe holidays. Let's start at the top. The charging floor, as it's called, is a platform level with the top of the furnace. This is where raw materials go in, iron ore, coke, and limestone in carefully calculated proportions. The coke is essentially purified coal that's been baked in special ovens to drive off impurities and volatile compounds. What remains is almost pure carbon, and carbon is what will pull the oxygen out of the iron ore, reducing it from iron oxide to metallic iron. The coke also provides the fuel, the heat source, that keeps the whole operation running. The limestone is flux. Its job is to combine with impurities in the ore, the silica and alumina and other compounds that would otherwise contaminate the iron. The limestone melts and forms slag, a glassy substance that floats on top of the molten iron, protecting it from oxygen in the air, trapping the impurities. The proportions matter enormously. Too much ore and the furnace runs cool doesn't fully reduce the iron. Too much coke and you waste fuel. And worse, the iron absorbs too much carbon and becomes brittle. Too little limestone and the slag doesn't form properly, impurities end up in the iron. Too much limestone and it insulates the charge, slows down the whole process. The furnace master is the man who determines these proportions. He's part chemist, part craftsman, part fortune teller. He knows his furnace the way a ship's captain knows his ship. He can tell by the color of the flame at the top whether the mix is right. He can tell by the smell of the gases whether he needs to adjust. He keeps notes, meticulous records of every charge, what went in, what came out, how long it took. The charging happens in a steady rhythm. Every hour or two, more material goes in the top. The exact timing depends on the size of the furnace, the quality of the ore, the temperature, 100 different variables. The men who do the actual charging work on the platform at the top, they wheel barrows of ore, coke, and limestone to the edge of the furnace mouth and dump them in. The heat rising from below is intense, scorching. Even in winter, these men work in just thin shirts, soaked through with sweat. In summer, it's almost unbearable. Some wear leather aprons to protect their legs and torsos from the radiant heat. Some wrap wet cloths around their heads. They develop a technique, a way of approaching the furnace opening, dumping the load, and stepping back quickly. Too slow and your clothes can catch fire from the heat alone. No flame necessary. Too fast and you might stumble, might fall, and falling near that opening means death, instant and certain. Inside the furnace, the materials descend slowly, taking hours to work their way from top to bottom. As they descend, they move through different temperature zones. Near the top, temperatures might be only a few hundred degrees. The materials dry out here. Any remaining moisture boils away as steam. Further down, temperatures reach 700 or 800 degrees. The limestone begins to decompose, releasing carbon dioxide. The coke starts to burn in earnest, though there's not enough oxygen yet for complete combustion. Lower still, we reach the heart of the furnace, where temperatures soar to 3,000 degrees Fahrenheit or more. At these temperatures, iron oxide cannot exist. The oxygen is ripped away by the carbon monoxide rising from the burning coke below. The iron melts, becomes liquid, begins to trickle downward through the mass of coke and limestone. The chemical reactions are complex, but the basic process is this. Carbon from the coke combines with oxygen from the air blasted in at the bottom to form carbon monoxide. The carbon monoxide then steals oxygen from the iron ore, reducing iron oxide to metallic iron and converting itself to carbon dioxide in the process. Some of the carbon dioxide reacts with more coke to form more carbon monoxide, and the cycle continues. The iron absorbs some carbon as it trickles through the coke. This is actually desirable up to a point. Pure iron is relatively soft. Iron with 3 or 4% carbon is much harder, more useful for casting. This high carbon iron is what we call pig iron. At the very bottom of the furnace is the crucible, a wide basin where the molten iron collects. The slag floats on top of the iron because it's less dense. Through small openings called tuyères, blowers force air into the bottom of the furnace. This air is what feeds the combustion, what keeps the temperatures high enough to melt iron. The blowers in the 19th century were massive affairs. Early on, water wheels powered them, later steam engines. Enormous leather bellows, or later, piston-driven cylinders that forced air through pipes into the furnace. The air might be cold or, in more advanced operations, preheated using waste heat from the furnace itself. Preheating the air increased efficiency dramatically, meant you could produce more iron with less coke. The blast of air entering the furnace created the distinctive roar that gave the blast furnace its name, a sound like a perpetual windstorm, like standing too close to a waterfall. Men working near the furnace learned to read lips because shouting was useless. Your voice just disappeared into that roar. Every 12 hours or so, the furnace needed to be tapped. This meant opening a hole at the bottom of the crucible and letting the molten iron run out. The tap hole was normally sealed with clay, packed tight. When it was time to tap, a man would drill through the clay with a long iron bar until he broke through. The moment the hole opened, molten iron began to pour out. Liquid iron at 3,000 degrees, glowing white at the center, orange at the edges, flowing like water but weighing half a ton per cubic foot. It ran along channels carved in sand on the floor of the cast house, the building adjacent to the furnace. These channels were called sows and pigs, which is where the term pig iron comes from. The main channel, the sow, ran the length of the cast house. Smaller channels branched off at right angles, pigs. The iron filled the sow first, then flowed into the pigs, cooling and solidifying as it went. The men in the cast house worked in hell itself. The floor radiated heat from the molten metal. The air was thick with fumes, sulfur, and carbon monoxide, and compounds that probably didn't even have names yet. The light from the glowing iron was so bright it hurt to look at directly. Men wore dark glasses, primitive things made of smoked glass, to protect their eyes. They used long tools, rakes, and hoes and bars, all on extended handles to guide the flow of iron, to break up dams of cooled metal, to skim slag off the surface. Every movement was practiced, economical. You didn't make unnecessary motions near molten iron. You didn't take chances. After the iron came the slag. The tap hole was positioned so that iron, being denser, flowed out first. Once the iron level dropped below the opening, slag began to pour out. The slag was tapped into separate channels, guided into pits where it would cool and solidify. Some mills had uses for slag. It could be crushed and used for road building or ground fine and mixed into cement. But mostly it was just waste, glassy black rock that piled up in enormous heaps beside the furnaces. Once the crucible was empty, or near enough, the tap hole was plugged again. A man would approach with a ball of clay on the end of a long pole and ram it into the hole until the flow of metal stopped. Then more clay, packed and tamped, building up layers until the seal was solid. And then it all began again. More ore, more coke, more limestone dumped in at the top. The furnace never rested. The men who worked the blast furnace were a distinct class within the mill. Furnace keepers, they were called, or sometimes just furnace men. They were proud of their skills, protective of their knowledge. A good furnace keeper could coax more iron from a given amount of ore than a poor one, could keep the furnace running smoothly while a poor one let it clog or cool. They passed their knowledge on carefully, selectively. A master furnace keeper might take on an apprentice, a young man who would spend years learning the craft, learning to read the color of the flame, to judge the consistency of the slag, to know by sound alone whether the furnace was running properly. It was dangerous work, certainly. Men died regularly. Burns were common, everything from minor to fatal. The gases from the furnace were poisonous. Carbon monoxide had no smell, no warning. Men simply collapsed sometimes, overcome by fumes they never knew were there. But it was also prestigious work in its way. A furnace keeper earned more than a common laborer, had more security, was treated with more respect. In the rigid hierarchy of the mill, he occupied a middle tier, above the unskilled workers, below the managers and owners, but distinct from both. The blast furnace represented humanity's ability to command fire, to reshape the earth itself. It was terrifying and magnificent in equal measure, and it never, ever slept. The iron that flows from the blast furnace is called pig iron, and while it's useful for some purposes, it's not ideal for most. It contains too much carbon, typically 3 to 4%, which makes it hard but also brittle. Drop a bar of pig iron, and it might shatter like glass. Try to bend it, and it snaps. For most applications in the 19th century, what you wanted was wrought iron. Wrought iron contains less than 0.1% carbon. It's much more ductile, meaning it can be bent and shaped without breaking. It's more malleable, meaning you can hammer it and forge it. It's the iron you want for chains and nails and horseshoes and railroad tracks and ship hulls and 1,000 other things. Converting pig iron to wrought iron meant removing most of that carbon, and this was done in a process called puddling. The puddling furnace was its own kind of hell. different from the blast furnace, but no less demanding. A puddling furnace was much smaller than a blast furnace, low and rectangular, perhaps 10 feet long and 4 feet wide. The hearth, where the iron melted, was lined with iron oxide and slag, materials that would donate oxygen to help burn out the carbon. The furnace was heated by coal burning in a separate firebox, with flames directed across the top of the hearth. The puddler, the man who operated the furnace, began by charging it with broken pieces of pig iron, perhaps 400 or 500 pounds at a time. He closed the door and stoked the fire, bringing the temperature up until the pig iron melted into a pool about 6 inches deep. And then the real work began. As the molten iron heated, carbon in the iron began to combine with oxygen in the furnace lining and in the air, forming carbon monoxide and carbon dioxide. This oxidation process was called refining, and the puddler had to manage it carefully. He did this with a long iron bar called a rabble, perhaps 8 feet long, with a blade on the end. Through a small door in the front of the furnace, he thrust this rabble into the molten iron and stirred. Stirring molten iron is exactly as nightmarish as it sounds. The heat coming through that small door was intense enough to singe hair and eyebrows. The rabble became red hot within seconds. The puddler had to stand to the side, as far from the door as the length of the rabble would allow, and still the heat was overwhelming. He stirred continuously, or nearly so, for perhaps an hour and a half. Stirring brought fresh iron to the surface where it could contact oxygen. Stirring distributed heat evenly through the bath. Stirring prevented the iron from solidifying unevenly. His arms were in constant motion, pushing the rabble in, dragging it back, stirring in circles, scraping the bottom, bringing up material that had settled. The weight of the rabble, the resistance of the thick molten iron, the heat, the continuous exertion. It was exhausting in a way that's hard to comprehend. Puddlers were typically the most physically fit men in the entire mill. They had to be. They developed enormous upper body strength, shoulders and arms and backs like draft animals. They also didn't last long. A man might puddler for 10 or 15 years before his body gave out, before his strength failed or his lungs succumbed to the constant inhalation of fumes. As the carbon burned out of the iron, the melting point increased. Iron with high carbon content melts at relatively low temperatures, around 2300 degrees. Pure iron doesn't melt until nearly 2800 degrees. As the carbon decreased, the iron began to thicken, to become pasty rather than liquid. The puddler watched for this change, felt it in the resistance of the rabble. When the iron reached the right consistency, thick and sticky, he began the next phase, which was gathering. Using the rabble, he pushed and scraped the pasty iron together into a large ball, a bloom weighing perhaps 150 pounds. This required skill and strength in equal measure. The iron wanted to stick to the hearth, to the walls, to itself in irregular lumps. The puddler had to work it, knead it almost, bringing it together into a coherent mass. Once the bloom was formed, he used the rabble to roll it toward the door of the furnace. Then, with the help of an assistant, he extracted it. The bloom came out glowing orange, dripping with slag, radiating heat. Using long tongs, they carried it quickly to a nearby shingling hammer. The shingling hammer was a massive mechanical hammer, powered by a water wheel or steam engine with a head that might weigh several 100 pounds. The bloom was placed on the anvil beneath this hammer, and the hammer was set in motion. Wham, wham, wham. Each blow compressed the iron, squeezed out trapped slag, consolidated the structure. The force of the blows created showers of sparks, sent pieces of slag flying, made the ground shake. The bloom was turned and repositioned repeatedly, hammered from all sides until it formed a rough rectangular bar. This bar, still red-hot but now solid, was called a merchant bar, and it was the basic product of the puddling furnace. It could be sold as is or further processed, depending on the customer's needs. A good puddler could produce 3 or 4 blooms in a 12-hour shift. Each bloom represented nearly 2 hours of continuous, exhausting labor. And the heat, always the heat. Puddlers drank enormous quantities of water, gallons per shift, and still they became dehydrated. They lost weight over the course of a shift, literally sweated away pounds. Many puddlers became alcoholics, drinking not for pleasure but for the calories, for the liquid, for something to blunt the constant pain in their joints and muscles. Many died young, of lung diseases, of heart failure, of simple exhaustion. But the work was essential. Without puddling, there was no wrought iron. Without wrought iron, the Industrial Revolution would have stalled. Everything from railroads to buildings to machinery depended on materials that could be produced only through processes like this, processes that consumed men as readily as they consumed coal. The puddling furnace had to be maintained constantly. The lining wore away, eroded by the heat and by the chemical reactions taking place. After a certain number of heats, the furnace had to be shut down, cooled, and relined. This was skilled work in itself, requiring knowledge of how to mix the right materials, how to apply them, how to dry them properly before the furnace was reheated. Some mills operated dozens of puddling furnaces simultaneously, each with its own puddler, each producing blooms in an endless rhythm. The noise was constant. The hammering of the shingling hammers, the roar of the fires, the shouts of men communicating over the din. The blooms, once formed, went to the rolling mill, where they would be further refined and shaped. But that's the next part of our story. For now, let's linger here a moment longer, in the puddling shed, in the heat and the noise and the ceaseless labor, because this was the heart of iron making for much of the 19th century. This was how it was done, how men transformed brittle pig iron into workable wrought iron hour after hour, shift after shift, year after year. The merchant bars from the puddling furnace still aren't finished products. They're rough, uneven, still need to be shaped into usable forms. Rails for railroads, plates for ship hulls, rods for making wire, beams for construction. This work happened in the rolling mill, and while it wasn't quite as hot as the puddling shed or the blast furnace, it had its own particular dangers, its own demands. The rolling mill was a building filled with massive machines, machines that could only have been invented in an age that had lost its fear of iron. Imagine cylinders of solid steel, perhaps 2 feet in diameter and 6 feet long, mounted horizontally in heavy iron frames. These cylinders, called rolls, turned in opposite directions, and anything placed between them was squeezed, compressed, elongated. The power required to turn these rolls was enormous. Water wheels in earlier mills, steam engines later, Shafts and gears and belt drives transmitted power from the engine to the rolls, and the whole building shook and vibrated when the mills were running. The floor itself seemed alive, thrumming with mechanical energy. The process began at the reheating furnace. The merchant bars from the puddling shed had cooled during transport and hammering. They needed to be brought back up to working temperature, somewhere around 2,000 degrees. Hot enough to glow orange-white, hot enough to be plastic under pressure. The reheating furnaces were long and low, heated by coal or coke, with doors along one side. Bars were pushed in with long poles and left to heat for perhaps 30 minutes or an hour, depending on their size. Workers called heaters monitored the furnaces, watching through small openings, judging by color and experience when each bar was ready. When a bar reached the right temperature, it was pulled from the furnace using long tongs. 2 men typically handled this, one on each end of the bar, moving quickly but carefully. The bar was rushed to the first set of rolls, perhaps 30 feet away. Time mattered because the bar was cooling constantly, losing workability with every second. The bar was fed between the rolls, which caught it and pulled it through, squeezing it thinner and longer. The rolls might reduce the thickness by 10 or 20% in a single pass. The bar came out the other side, moving fast, still glowing, and another set of workers caught it with tongs and guided it. Here's where it got interesting. The bar was now longer than it had been, sometimes much longer. A bar that went in 8 feet long might come out 10 or 12 feet long, and it was still thick enough to need more passes through the rolls. So the bar was flipped over, rotated 90 degrees, and fed back through the same rolls or through a second set of rolls with a slightly smaller gap. Each pass made the bar longer and thinner. Each pass required coordination between multiple workers, timing, strength, attention. The rhythm of a rolling mill was almost musical in its way. The rumble of the rolls, the clang when a bar was dropped under the rollers, the hiss of steam if water touched hot metal, the shouts of the workers communicating over the noise, and underlying it all, the constant shake and vibration of the building itself. As the bar lengthened, it became harder to control. A 20-foot bar of hot iron, emerging from the rolls at speed, could whip around if not guided properly, could injure or kill anyone in its path. The workers developed techniques, ways of guiding the bar using poles and hooks, keeping it straight, preventing it from curling or bending. The bar made multiple passes, 6 or 8 or more, until it reached the desired dimensions. A merchant bar might start at 6 inches by 6 inches in cross-section and end at 1 inch by 1 inch, but 40 or 50 feet long, or it might be rolled flat into plate, half an inch thick and 2 feet wide. For rails, the process was similar, but the rolls had grooves cut into them, negative profiles of the rail shape. The bar was passed through progressively shaped grooves, each one forming the iron closer to the final rail profile. This required incredibly precise machining of the rolls themselves, and the rolls wore out over time, had to be removed and either remachined or replaced. The workers in the rolling mill were called rollers, and like the puddlers, they were a skilled and distinct class. The roller in charge of a particular mill, the rougher, or the finisher, depending on which set of rolls he operated, earned good wages and had considerable prestige. His assistants, the catchers and turners and helpers, earned less, but were learning the trade, working their way up. The work was dangerous in ways that weren't always obvious. The rolls themselves could catch clothing or flesh if you got too close. Men lost fingers, hands, entire arms to the rolls. The hot bars could burn, obviously, but they could also strike like whips if they got away from the workers guiding them. Men were killed by flying bars, by bars that curled back unexpectedly, by any number of accidents that happened too fast to prevent. And then there was the scale. When iron is heated to high temperatures and exposed to air, the surface oxidizes, forms a thin layer of iron oxide. This scale flakes off when the iron is worked, when it passes through the rolls, or when it's hammered. The scale flew through the air like tiny red-hot shrapnel, embedding itself in skin and clothing. Workers wore thick leather aprons and gloves, but scale still found its way in, left tiny burn marks that scarred over. The noise of the rolling mill was intense enough to cause permanent hearing loss. Many rollers in their 40s or 50s were partially deaf, communicated as much by gesture and lip reading as by speech. The combination of noise, heat, heavy labor, and constant danger created an environment that aged men rapidly. Once a bar or rail or plate was rolled to the correct dimensions, it was marked with the mill's stamp, sometimes the date, sometimes a heat number for quality control. Then it was moved to the cooling yard, where it was laid out in long rows to cool slowly. Rapid cooling could cause cracking or warping, so the iron was allowed to cool naturally over hours or days depending on its thickness. The cooling yard was an odd place, quieter than the rest of the mill, filled with rows upon rows of iron in various stages of cooling. The newest pieces still glowed dull red in dim light. Pieces that had been there for hours were black, but still hot to the touch. Only pieces that had cooled overnight were safe to handle with bare hands. Workers in the cooling yard sorted and stacked the finished products, preparing them for shipment. This was considered relatively light work, though it still involved moving heavy pieces of iron around. Older workers, men whose bodies had broken down in the harder jobs, often ended up in the cooling yard, grateful for work that didn't require the strength or stamina they no longer had. From the cooling yard, the iron went to customers. Rails went to railroad companies, plate to shipbuilders, rods to wire manufacturers, bars to blacksmiths and fabricators. Each piece represented hours of labor, tons of coal and ore, the coordinated effort of dozens or hundreds of workers across multiple stages of production. And every piece was unique in subtle ways. No two heats of iron were exactly identical. The ore varied slightly, the amount of carbon varied, the exact temperature of rolling varied. Experienced workers could sometimes tell by looking at a piece of iron where it had been made, what mill, even which furnace, based on subtle characteristics of color and texture and the way it had scaled. The rolling mill ran in shifts, typically 2 shifts of 12 hours each, sometimes 3 shifts of 8 hours in mills that operated around the clock. The changeover between shifts was a brief moment of chaos, one crew leaving, another arriving, information being passed along about which furnace was running hot, which set of rolls needed adjustment, which bars were giving trouble. The men walked home in groups, still covered in scale and soot and sweat, too tired sometimes to talk, just putting one foot in front of the other. They lived in company housing often, rows of identical houses within walking distance of the mill. Houses that shook when the mill was running. Houses where the windows were permanently filmed with soot. Houses where the laundry hanging outside collected a fine layer of iron dust before it could dry. Their wives boiled water for baths, scrubbed clothes that would never truly be clean, cooked meals heavy with potatoes and bread and whatever meat they could afford. The children played in streets where the air tasted of coal smoke, grew up with the mill's rhythm as the backdrop to their entire lives. Many of them would end up in the mill themselves, following their fathers, learning the same trades, perpetuating the same cycles. Everything we've discussed so far has been about iron, wrought iron, and pig iron, but not steel. Steel is something different, something more refined, more difficult to produce, and infinitely more valuable in the 19th century. Steel is iron with a carefully controlled amount of carbon, typically between 0.2 and 2%. Less than that, and you have wrought iron. More than that, and you have cast iron. That narrow range is what gives steel its remarkable properties. Harder than wrought iron, but not brittle like cast iron, able to hold an edge, able to be tempered and hardened. For most of human history, steel was produced in tiny quantities, laboriously, by craftsmen who worked by feel and experience. A blacksmith could make steel by carburizing wrought iron, by heating it in contact with carbon and letting carbon slowly diffuse into the surface, or by decarburizing cast iron, burning out excess carbon through repeated heating and hammering. Both processes were slow, unpredictable, produced only small amounts. That began to change in 1740 when Benjamin Huntsman developed the crucible process. The crucible process allowed steel to be made in somewhat larger quantities with more consistent quality, and by the 19th century, it was the primary method for producing high-quality steel. The process started with blister steel, which was wrought iron that had been carburized, heated for days in contact with charcoal until it absorbed carbon. The blister steel was broken into small pieces, sorted by quality, and placed in clay crucibles. These crucibles were ceramic vessels, roughly the shape of a tall bucket, perhaps 14 inches high and 9 inches in diameter, with a capacity of about 60 pounds of steel. The crucibles themselves were works of art, made from carefully selected clays mixed with ground-up old crucibles, shaped and fired in special kilns. A good crucible could survive several uses before cracking. A poor one might fail on its first heat, spilling molten steel and potentially causing disaster. The crucibles, filled with blister steel pieces, were placed in a special furnace, a crucible furnace, perhaps a dozen or more crucibles at a time. The furnace was fired with coke, and the crucibles were heated gradually, carefully, over several hours until the steel inside melted. Getting the temperature right was crucial. Too cool and the steel wouldn't fully melt, would remain pasty and heterogeneous. Too hot and the crucibles might fail, or the steel might absorb impurities from the crucible walls, or carbon might burn out unevenly. The furnace tenders watched constantly, adjusting airflow, adding fuel, monitoring the color of the flames, the appearance of the crucibles through small viewing ports. When the steel was fully molten, it was held at temperature for a time to allow impurities to rise to the surface where they could be skimmed off. The exact holding time depended on the quality of the starting material, the intended use of the finished steel, the experience and judgment of the steelmaker. Then came the pour. Using long tongs, workers lifted the crucibles from the furnace one at a time. The crucibles were glowing orange, nearly white in places, radiating intense heat. The workers carried each crucible to a mold, a cast iron mold the shape of an ingot, perhaps 2 feet long and 4 inches square in cross-section. The pour had to be steady, controlled. Too fast and the steel splashed, formed bubbles and voids in the ingot. Too slow, and the steel began to solidify and the crucible became viscous, difficult to pour completely. The worker tilted the crucible, and liquid steel, glowing brilliant yellow-white, flowed out in a stream, filling the mold from bottom to top. The sight was mesmerizing. Liquid steel is brighter than liquid iron, hotter, more fluid. It seemed almost alive as it flowed, rippling with heat distortion, sending up waves of warmth that made the air shimmer and warp. The molds had to be carefully positioned because once the pour started, it couldn't be stopped or corrected. Any mistake meant ruined steel, wasted time and materials, possibly a dangerous spill. As the molds filled, the steel began to cool and solidify almost immediately at the edges, in contact with the cooler iron of the mold. But the center remained molten for minutes, sometimes longer. The steel contracted as it cooled, and if cooling was too rapid or uneven, the ingot could crack, could develop internal stresses that made it useless. The ingots were left in the molds for a time, then removed while still red-hot and stacked in special pits or ovens where they could cool slowly, evenly, over many hours. This annealing process relieved internal stresses, helped produce a more uniform structure in the steel. The crucible process was expensive. It required skilled workers, high-quality raw materials, expensive crucibles that wore out regularly, and careful attention at every stage. The resulting steel was correspondingly valuable, used for tools, for springs, for anything that required hardness and resilience. Cutlery makers, tool makers, watchmakers, they all demanded crucible steel. But crucible steel production was limited in scale. Each crucible held only 60 pounds or so. Even a large furnace with many crucibles could produce only a few thousand pounds per day. For true mass production of steel, something else was needed, and that something arrived in the mid-1850s with the Bessemer process. Henry Bessemer's innovation was brilliantly simple in concept, though challenging in execution. Instead of slowly removing carbon from pig iron through puddling, or carefully adding carbon to wrought iron through cementation and melting, why not blast air through molten pig iron and let the oxygen in the air burn out the excess carbon directly? The Bessemer converter looked like an enormous pear-shaped vessel, 10 or 12 feet across, made of iron plates lined with refractory materials, mounted on an axle so it could be tilted. The vessel held perhaps 20 tons of molten pig iron, delivered directly from the blast furnace while still liquid. Once the converter was filled and tilted upright, air was blasted up through the molten iron from the bottom, through small holes called tuyères. The air pressure had to be high enough to penetrate the molten metal, which meant powerful steam-driven blowers. What happened next was spectacular and somewhat terrifying. The oxygen in the air immediately began reacting with carbon, silicon, manganese, and other impurities in the pig iron. These reactions were violently exothermic, meaning they released enormous amounts of heat. The temperature of the molten iron actually increased, even though heat was being lost to the surroundings. Flames shot from the mouth of the converter, sometimes 20 or 30 feet into the air. These flames changed color as the process progressed. At first, they were yellowish-white, bright and smoky, as silicon and manganese burned out. Then they became clearer, more intense, as carbon began to burn. The flames roared like a blast furnace like a rocket engine, an unholy sound that could be heard for miles. The entire converter glowed, the iron shell itself becoming red hot from the heat inside. Sparks and droplets of molten metal flew from the mouth, cascading down the sides, spattering the floor of the converter shed. The light was intense enough to cast shadows in broad daylight, to be visible at night from anywhere in the city. The blow, as it was called, lasted about 15 or 20 minutes. Workers watched the flames, judged by color and character, when the carbon had burned down to the right level. Too long, and you removed too much carbon, produced iron rather than steel. Too short, and you left too much carbon, produced something more like cast iron. At the right moment, the air blast was shut off. The converter was tilted, and the molten steel poured out into a ladle, an enormous bucket-like vessel that could be moved by crane. Before pouring, or sometimes in the ladle, additions were made. Spiegeleisen, an alloy of iron, manganese, and carbon, was added to reintroduce a controlled amount of carbon and manganese to produce steel of the desired composition. From the ladle, the steel was poured into molds to form ingots, just like crucible steel, but on a vastly larger scale. A single Bessemer converter could produce 20 tons of steel in under an hour. Multiple converters operating in shifts could produce hundreds of tons per day. The scale was revolutionary, and the cost of steel plummeted. But Bessemer steel had problems initially. It worked well with some ores, but not others. Phosphorus, a common impurity in many iron ores, couldn't be removed by the Bessemer process, and phosphorus made steel brittle and weak. It took years of experimentation, new furnace linings made of basic rather than acidic materials, before the phosphorus problem was solved. The open hearth process, developed around the same time, offered an alternative. The open hearth furnace was a large, flat hearth where pig iron, scrap steel, and iron ore were melted together and refined over the course of several hours. It was slower than the Bessemer process, but more controllable, better able to handle impure raw materials, capable of producing larger batches of more uniform quality. Open hearth furnaces were enormous structures, 50 or 60 feet long, with regenerative chambers underneath that preheated the incoming air and fuel using waste heat from the exhaust. The regenerators were filled with brick checkerwork, thousands of bricks arranged with gaps between them to maximize surface area. Exhaust gases passed through one set of regenerators, heating the bricks. Then flow was reversed, and incoming air passed through the heated bricks, raising its temperature to well over 1,000 degrees before it even reached the furnace. This preheating dramatically improved fuel efficiency and raised the furnace temperature high enough to melt steel and scrap together. The furnace could run on either gas or liquid fuel, and the flames played across the surface of the molten bath, transferring heat, promoting the oxidation reactions that refined the steel. Charging an open hearth furnace was a major operation. Doors on the front of the furnace opened, and charging machines on rails ran forward, carrying boxes full of pig iron or scrap. The boxes tipped, dumping their contents onto the hearth, and the machines quickly withdrew before the heat became unbearable. This was repeated until the furnace held the desired amount of material. As the charge melted, samples were taken periodically using long-handled ladles. A bit of steel was scooped from the surface, poured into a small mold, allowed to cool slightly, then examined. Experienced steelmakers could judge by appearance, by the way it fractured when broken, what the composition was and whether the steel was ready. Chemical analysis became more common as the 19th century progressed, but judgment and experience remained crucial. When the steel was ready, a tap hole at one end of the furnace was opened, and the steel flowed out into ladles just like the Bessemer converter. The ladles, carried by overhead cranes, transferred the steel to molds or, in later operations, to continuous casting machines. The scale of late 19th century steel production was staggering compared to anything that had come before. Mills that had once produced a few hundred tons of iron per year were producing thousands of tons of steel per week. The material that had once been precious, reserved for special applications, became commonplace, the foundation of bridges and buildings and railroads and ships. The steel ingots from the Bessemer converters or open hearth furnaces were just the beginning of another journey. These ingots, weighing perhaps 1,000 pounds each, had to be reheated and shaped into usable forms, and this work took place in rolling mills even larger and more powerful than those used for wrought iron. The ingots went first to soaking pits, large furnaces, where they were heated slowly and evenly to rolling temperature. The word soaking is apt because the ingots sat in these furnaces for hours, allowing heat to penetrate uniformly throughout their mass. Rapid heating would have left the interior cool while the surface became too hot, leading to cracking and defects during rolling. The soaking pits were arranged in long rows, each pit holding several ingots stacked vertically. Gas flames heated the pits from below and from the sides, and the temperature was carefully controlled. Too hot, and the steel began to oxidize excessively, forming thick scale that was wasteful and difficult to remove. Too cool, and the steel wasn't plastic enough for rolling. When an ingot reached temperature, glowing orange-white through the observation ports, it was lifted from the pit using overhead cranes. These cranes were massive structures capable of handling loads of several tons, running on rails mounted high on the walls of the building. The crane operator sat in a cab suspended from the crane, controlling movement with levers and handles, guiding the crane and its load with a precision that seemed impossible given the scale of the equipment. The glowing ingot was placed on a transfer car, a heavy rail-mounted cart that carried it to the first set of rolls. These were roughing rolls, massive cylinders, perhaps 3 feet in diameter, capable of exerting hundreds of tons of pressure. The ingot passed between them was squeezed and elongated, emerged longer and thinner on the other side. Unlike the rolling of wrought iron bars, the rolling of large steel ingots required immense power and robust equipment. The mills shook the ground when they ran. The building itself, constructed of heavy timber and iron, creaked and groaned under the forces involved. The noise was beyond description, a combination of rumbling, grinding, and occasional bangs when the ingot entered the rolls, or when equipment adjusted. The ingot made multiple passes, turned and rotated between passes, gradually approaching the desired shape. For structural beams, I-beams, and H-beams, the rolls had grooves cut into them, progressively shaped profiles that formed the steel into the characteristic shapes. For plates, flat rolls squeezed the ingot into sheets of uniform thickness. The skill involved in operating these mills was considerable. The roller had to judge the temperature of the steel by eye, the orange-white glow that indicated proper working temperature gradually darkening toward red as the steel cooled. He had to adjust the spacing between rolls, coordinate with the crew feeding and catching the steel, maintain the rhythm of the operation. The steel cooled as it was worked, and there was only so much rolling that could be done before the steel became too stiff, too cool to shape properly. At that point, the steel went back into a reheating furnace for another soaking, then back to the rolls. A large beam might require 3 or 4 reheatings before it reached final dimensions. Once rolled to size, the beams or plates or rails went through finishing operations. Saws cut them to specified lengths, massive friction saws or later shears that could cut through steel inches thick. The cut surfaces were often rough, had to be ground or machined smooth for certain applications. Holes were drilled for bolts or rivets. Stamps marked the steel with information about its grade, its source, sometimes the date of manufacture. Quality inspections checked for cracks, for dimensional accuracy, for hardness, and other properties. And then, finally, the steel was ready for shipment. Rails loaded onto flat cars, destined for railroad construction sites across the country. Beams bundled and strapped, bound for bridge builders and construction companies. Plates stacked and secured, heading to shipyards where they would become the hulls of vessels. Each piece of steel represented an astonishing accumulation of labor and energy. The ore mined from the earth, transported to the mill, smelted in the blast furnace, converted to steel, reheated, rolled, finished. Every step required fuel, coal, or coke burned in quantities that are difficult to imagine. Every step required human effort, men working in heat and noise and danger. The environmental impact was staggering, though nobody thought in those terms at the time. The smoke from the furnaces and mills blackened the sky, deposited soot on everything. Within miles, the rivers that provided water for cooling and power ran red with iron oxide, poisoned with chemicals. The slag heaps grew into artificial mountains, stark and barren landscapes of glassy black rock where nothing would grow for decades. The human cost was equally staggering. Men were injured constantly, burns, crushed fingers and hands, broken bones from falling materials or moving machinery, lung diseases from inhaling dust and fumes. Some injuries were minor, treated with a bandage and back to work the same day. Others were permanently disabling or fatal. There was no workers' compensation, no safety regulations to speak of, no assumption that the employer bore responsibility for workplace injuries. If you were hurt, you dealt with it. If you couldn't work anymore, you found something else to do, or you starved. Families depended on every wage earner, and the loss of a father's income could mean catastrophe. Children pulled from school to work, eviction from company housing, descent into desperate poverty. Yet the men took pride in their work. The skills they developed, the knowledge they accumulated, these were valuable and respected. A master roller or furnace keeper could find work anywhere there was a mill. He could command decent wages, provide reasonably well for his family, hold his head up in the community. The culture of the mills was its own thing, separate from the outside world. The men developed bonds, friendships, forged in shared hardship and danger. They looked out for each other, taught newcomers the tricks of survival, maintained codes of behavior and honor that might seem strange to outsiders, but made perfect sense within the context of the mill. They had their own language, specialized terms for tools and processes and situations. They had their own rhythms, the patterns of shifts and days off, of paydays and slack times. They had their own social hierarchies, distinctions of skill and experience that mattered more within the mill than distinctions of birth or education mattered outside. The mills never truly stopped. Even when production paused for maintenance or lack of orders, there was always work to be done, furnaces to reline, equipment to repair, yards to organize, 1,000 tasks that kept men employed and kept the mill ready for the next campaign of production. At night, the mills glowed like cities of fire. The blast furnaces with their perpetual flames at the top. The open hearth furnaces with their periodic taps, releasing rivers of molten steel. The Bessemer converters with their spectacular blasts of flame. The rolling mills with their glowing ingots emerging from the soaking pits. All of it created a landscape of light and shadow, heat and darkness that existed nowhere else on earth. From a distance, it could be beautiful in its way, the glow against the night sky, the silhouettes of structures and equipment, the occasional shower of sparks. Close up, it was hell, the heat, the noise, the danger, the endless, exhausting labor. But this was how it was done. This was how humanity learned to produce steel in industrial quantities, how we built the modern world. Every railroad, every bridge, every building with a steel frame, every ship with a steel hull, all of it depended on processes like these, on men willing to work in conditions we can barely imagine, for wages that seem pittance now, but were survival then. The steel cooled slowly in the yards, clicking and ticking as it contracted, the internal stresses adjusting and settling. The workers finished their shifts and walked home, too tired to do much more than eat and sleep before returning to do it all again. The blast furnaces roared on through the night. The puddlers stirred their heats. The rollers guided glowing bars through the mills. The rhythm continued, unchanging, inexorable, the heartbeat of industry. And somewhere, a steel beam that began as ore in the ground months ago finally cooled to ambient temperature, ready to be shipped, ready to become part of something larger, a building that would stand for a century, a bridge that would carry thousands of people across a river, a rail that would guide trains across a continent. The journey complete, the transformation absolute, rock to metal, earth to civilization. All of it built on fire and sweat and the willingness of human beings to endure what should not be endured, to work in conditions that should not exist, to make possible what had previously been impossible. This was the 19th century steel mill. This was how it was done. And now, as the story comes to its close, as the final beam cools and the night shift begins another cycle, you can rest, knowing every exhaustive detail of this incredible, terrible, magnificent process. Sleep well.